Hello guys, this is a tutorial to tell you about interference of light. Interference of light is simply when only two light waves superpose in space. So they make something called interference of light. Listen please or see this figure, it is very important. This is a laser light. Here we have a plane containing two slits. As we know from diffraction, each slit will re-emit light coming again as a wave. So in this area, the two waves superpose. So we say that this is the region of interference. This black line represents a screen such that we can observe the interference pattern on it. This here we will not observe interference and there, so we will observe it only here where the two waves superpose. This figure shows me the pattern of light and dark fringes or bright and dark fringes. This is what we will see on the screen. We will see bright and dark fringes, etc. Now, to obtain this figure, we have some properties or some conditions in order to observe this pattern. Now we have two conditions the coming light must satisfy in order to observe this stable pattern. First, the two waves must have the same frequency. If the two waves have different frequencies, then we will not observe this pattern. Second, the two waves must be coherent. What is meant by coherent? Coherency means that when you have two waves, either they are in phase or they have a difference in the phases between them, but this case must be stable with time. So if they start at these 2 points as in phase, they must remain in phase. And if there is a phase difference between them, the phase difference must remain constant. If this condition is satisfied, then we will observe a stable pattern, which means that here we will always see a light band or light fringe. Here we will always see a dark fringe. Otherwise, if the two waves are not coherent, what happens? Because of the variation in the phase difference, any point will become a light and dark fringes as time goes on and on. So in order to get in order to get a stable pattern of interference, then we must have two sources of same frequency and coherent. So in this setup, the two conditions are satisfied. Why? As you see, this is a laser light. When it reaches this point, it is divided by the two slits into two waves. So the same laser light is divided into two waves. Then the two waves are of same frequency because they are coming from the same source, and they are coherent because the same source is feeding them. In order to understand more and more why when we have one source then and divided into two sources, then the two sources are or must be coherent. Imagine you have a tuning fork. You know what is a tuning fork? It is a piece of iron of two ends. Now, if I hold this tuning fork by my hand and I vibrate it, oscillate it up and down on the surface of water, what happens? Then I have two sources of water waves. But these two sources are coherent and they are in phase because when one of them touches the surface of water, the second one also touches the surface of water at the same instant. So they are in phase. As I vibrate them with time, they produce the two coherent waves. But if I hold in my two hands, in each hand I hold one piece of iron, and then I oscillate them, let them to oscillate on the surface of water, I cannot ensure that the two waves are coherent, because as time goes on there must be a certain phase difference between the two sources, and this phase difference changes with time. Since it changes with time, then the two sources are not coherent. And now I can conclude that I don't have two separate sources which are coherent. Never. Now, to obtain two coherent sources, I must divide one laser source, as in this setup, into two sources, and then they give us two coherent sources. This is very, very important to know that coherent sources are obtained when I divide one source into two sources, then they are coherent, and at the same time they have the same frequency, so the conditions of interference are satisfied. This is why we observe on the screen a stable pattern of interference, a stable pattern. Let me see also this figure, it is very important. As you see, this is a source of light, red light. The light reaches this plane, double slit as you see. Here is the first slit which re-emits light again, and this is the second, also re-emits light, so they interfere at this area. Now, it is important to talk about the properties of the pattern. As you see, we have three properties. First, we have alternating bright and dark fringes, again as in diffraction. Alternating bright and dark fringes, as you see. Bright, dark, etc. Second property, they are equidistant. The distance from this one to here is the same as from here to there. It is totally different from diffraction. Here we have equidistant fringes. And the third property is that the pattern is parallel to the slits. Pattern is parallel to the slits. Now I can call this fringe as central, first bright, second bright, also first bright and second bright, etc. So we don't have a central dark fringe. We have only central bright fringe. So we call this first dark fringe, second dark fringe, and here first and second, etc. The important point is that to know that when I talk about a bright fringe, in reality I'm talking about the center of the bright fringe. So if I talk about this bright fringe, I'm talking about this point. This central fringe, I'm talking about this point. This dark fringe, I'm talking about this point, the center of the dark fringe also. Now, let me study interference from other point of view. This is a virtual laboratory, and I can observe it here. So this is the coming light. It reaches the plane of the double slit, and then interference is observed on this screen. This is the central fringe, bright fringe. This is a dark fringe, etc. And now I can change some properties, and you have to see it, it is very important. Now I can change the wavelength of the incoming light from 700, let me say, to 900 nanometers, or let me put it for 450 nanometers. It becomes blue, and as you see, the pattern changes. So the pattern, and we will talk about after a while, the pattern depends on the wavelength. Let me change it again to 700 and you will see the change. Second point is that the spacing between the slits. Here I have two slits. They are separated by a distance. We will call it small a. In the diffraction we call a as the width of the slit, but now we will use a as the distance between the centers of the two slits. Now I will increase the distance between the slits, and as you see, the pattern changes too. So now the pattern depends on both wavelength and the spacing between the slits, which is A, but there is a third variable, but I cannot change it from this laboratory because I cannot. Now you can see clearly the two slits, okay, because I move them away from each other. But the third property is that the distance separating this plane, the plane of the slits, from the plane of the screen, it is called capital D, and as we move the slit, the plane of the pattern or the screen away and away from this plane, the pattern becomes wider. This is because the angular width increases because of the distance, and then the pattern becomes wider and wider. So there are three important variables to remember: the wavelength of the incoming light, the spacing between the slits, and the distance separating the plane of the slits and the screen. Now it is important to observe the intensity. What happens to the intensity? Let me take a look here. As you see, this is the pattern that we saw before in the figure. Now you see that the fringes are equidistant. They are parallel to the slits, and they are rectilinear, and they are alternating, bright, dark, etc. And at zero, what is zero? This is the point we observe a bright fringe. This is the central fringe. Don't forget that this, if we change something in this setup, for example, we move this plane to the right or to the left, then everything is changed. So to make a reference, this setup is called Young's experiment. Whenever I talk about Young's experiment, this means that this light reaches the midpoint of the two slits, and the slits are separated by A, and the distance between this and that is capital D, etc. And now we want to observe the intensity of light. What happens to the intensity? As you see, the intensity is the same at the midpoint of the fringes. At the central fringe, this is the intensity. At the maximum first bright fringe, it is of same intensity, and etc. This is because the superposition itself can interpret this. Why? At this point, what happens? A maximum from the source S1 meets with a maximum from the source S2. They are added up to give me a maximum. At that point, a maximum from S1 superposes with a minimum from S2 to give me zero intensity. So maximum, zero, maximum, zero. Here, a maximum meets a maximum. Here, a minimum meets a minimum. In light, we add in absolute value, so it gives me a maximum intensity. So maximum, 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 minimum, 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 maximum, and etc. So the intensity looks like this figure. And now we are going to study interference analytically. This figure must be memorized by all students. It is very, very important. Light comes from here, reaches this plane, S1 and S2. They are apart, because in order to see them clearly, the distance separating them is small a, and each one becomes a secondary light source. It gives light in this area. They superpose to give me interference on this screen. It is separated from the plane of slits by a distance capital D. And now the important point, which we will use it later, it is this axis, x prime O x. O is the origin of this axis, but it is placed at the point where the perpendicular bisector of S1, S2 meets the screen. This is O. And x, this axis x prime x, is directed upward. So all points above O have positive abscissa, and points below O have negative abscissa. This is a very important figure. You have to know it and to study the interference of light. As I said before, to determine the points of maxima and minima, where maximum and maximum meet, or minimum and minimum meet, or maximum and minimum meet, there is a new variable called optical path difference. We must know it very clear. Let me go here. Take on the screen an axis x prime O x, as I said before, such that the perpendicular bisector to S1, S2 intersects the screen at point O, and it is directed vertically upward. And now, the optical path difference at a point M on the screen, let me say this is M. It is any point but belongs to the region of interference. So I take this point M. Now, the optical path difference at a point M on the screen. What is the optical path difference? It is important to know that, as I said before, since the nature of M is decided if I know if a maximum from S1 meets a maximum from S2, or a minimum with minimum, or a maximum with maximum. So it depends on the distance covered by the wave from S1 to M, and on the distance covered from S2 to M. This is the variable that tells me about the nature of M. So it is very important to know what is the difference between the two paths at M. And also I will assume that S is a point here, which is the main source. Then S gives a wave to S1 and to S2. So let me follow this one, S to S1 and then from S1 to M, and from S to S2, then from S2 to M. So the difference between these two passes decides what is the nature of M, if it is a maximum or a minimum, or any point between the maximum and the minimum. Thus, we study the optical path difference at a point M on the screen. It is simply given by delta. We say delta M is the optical path difference at a point M. It is equal to SS2 plus S2M, which is the total distance covered by the lower ray, SS2 to, and then from S2 to M, minus SS1 plus S1M, minus the distance covered from S to from S to S1, then from S1 to M. Please remember that we always start with SS2, not with SS1. We always start with SS2 plus S2M, and then from SS1 to S1M. This is called the optical path difference at point M. So finally I can say, if I choose another point N, so the optical path difference at N will be SS2 plus S2N minus SS1 plus S2N. Going back to point M, the optical path difference at M, So delta M is equal to SS2 plus S2M minus SS1 plus S1M, which is equal also to SS2 minus SS1 plus S2M minus S1M. Now, listen please. In Young's experiment, since S is placed on this line, so SS2 is equal to SS1 only in Young's experiment. So what happens to this term? It vanishes. So finally I get, by definition, I get delta M to be S2M minus S1M. Now, going to this definition, important definition, the central fringe of a pattern is the point where the optical path difference vanishes. So delta central is equal to 0. And let S2M equal to D2 and S1M equal to D1. In this setup, which I call it Young's setup, now SS2 equals to SS1, which means that delta M must be equal to D2 minus D1. D2 minus D1 and SS2 minus SS1 is 0. This is delta M. In Young's experiment, at any point you choose on the screen, delta will be D2 minus D1, which is S2M or N or O or P, etc., minus S1, this point, O or P, etc. Now, geometrically, from this figure, we can show that S2M minus S1M is equal to AXM over D, which is not the proof of this one is not required here. But what is A and XM and D? A and D are known. This is A and this is D, and X is the abscissa of the point under study. So D2 minus D1 is AXM over D. And also, if you say that, if you study the path difference at point N, then you say delta N is equal to AXN over D. Delta O is AXO over D. Now, XM is the abscissa of a point M, and I will remind you that if M is above O, then XM is positive, and if M is below O, then XM is negative. And now, what are the important points? I have two very important points. If delta, if the optical path difference at a point M is equal to k lambda, which means that it is a multiple of lambda. For example, the first one, S2M, covers 10 lambdas to reach from S2 to M. And the first one, or second one, from S1 to M equals 8 lambda, which means that it takes 8 oscillations, 8 total oscillations from S1 to M, and 10 total oscillations from S2 to M, then the difference will be 2 lambda, which is 2 complete oscillations. What does it mean? If they complete 1 oscillation or 2 oscillations or 10 oscillations or etc., then maximum meets with maximum or minimum meets with minimum. Thus, you obtain a bright fringe. And for example, going back to this example, if the first one covers 10 lambdas and the second one covers 2 lambdas, 8 lambdas, then the difference is 2 lambda, which means that this is the fringe, bright fringe of order 2, since it is 2 lambda. On the other hand, before talking about the other point, let me take a special point. For k equals 0, x equals 0. X equals 0 is the position of O. O is this point. So O is a bright fringe of order 0. On the other hand, as I said before, if delta is equal to 0 here, then this point is central. So O is the central bright fringe. I'll repeat. How to determine the position of a bright fringe is by using this formula. xm equal to k lambda d over a. K belongs to z, which is from minus infinity to plus infinity, but whole numbers. Now, for k equal 1, for example, this is the first bright fringe. K equal 2, second bright fringe. But what's about k equal 0? K equals 0, then x will be equal to 0. This is the central fringe, because in this case, if k equals 0, then delta will be equal to 0. Delta is k lambda is equal to 0. This is delta. Then delta equal to 0. So what is delta equal to 0? It is the central fringe. So if k equals 0, delta equals 0, then this point is central fringe. And what is this point? Where is this point? If x equals 0, then it is O itself. O is the central bright fringe. And now, on the other hand, if AXM over D is equal to K lambda plus half lambda, let me write this one here. If delta M is equal to A, which is equal to AXM over D, is equal to K lambda plus half lambda, which means that the difference between the two rays, this one and that, is half lambda, which is half an oscillation, then we obtain a destructive interference, or maximum with minimum, which gives me zero intensity, and the point will be the center of a dark fringe of order K also. Finally, what is an interfringe? The interfringe, by definition, it is the distance between two consecutive fringes of same nature. Two consecutive fringes of same nature. So, let M and N be two consecutive bright fringes of orders K and K plus 1. M is of order K. The next one must have the order K plus 1. So simply I must be equal to xm minus xn. Or let me put this n and this is m. So n is of order K and m is of order K plus 1. So m is after n. Thus, I must be equal to xm minus xn. It is k plus 1 lambda d over a minus k lambda d over a. Then it is equal to lambda d over a. This is the interfringe that separates two fringes, consecutive fringes of same nature. So I is the distance from this point to that point, or from this point to that point. This is I.